So now let's look at some application problems. Suppose that a construction zone can allow 50 cars per hour to pass through, and that cars are arriving at a random rate of X cars per hour, and that the average number of cars waiting in line to get through the construction zone can be estimated by the function n of x equals x squared divided by 2500 minus 50x. So what are we learning from that? All that. Well, a construction zone is letting 50 cars pass through this section every hour. And we can make a model that takes however many cars are being added every hour and show what the average number of cars waiting in that line is going to be as a result of that, given by the function. So the first thing we might want to do is we might want to label these axes on the graph on the right. The x-axis, as it said in the problem, is the rate of cars per hour. Rate of cars per hour. So that's the number of cars that are adding into the line, whether it be there's only 1 car per hour passing through the area, maybe it's not that busy, or we have a very busy city street where there's maybe 40 cars entering the zone per hour. And the output, that n of x, is telling us the number of cars waiting in line, and that's from that last sentence of the problem, the average number of cars waiting in line. So we'll put that for the y, or in this case, the n-axis. Number of cars waiting in line. And so that's what our model is. For part A, they want to get some inputs and some outputs. They're going to evaluate for 20, 40, and 49. And what does that mean? It means that if 20 cars are coming in, if 40 cars are coming in, if 49 cars are coming in, how many cars on average are waiting in line at any given time? So they went ahead and plugged that in for you. When you get 20, when you plug in 20, you get 4/15. When you plug in 40, you get 3.2. And when you plug in 49, you get 48. So if 20 cars are coming in on the hour, then on average, you have less than a car waiting in line at any given time. So that might be just because the rate at which they're letting cars through is pretty close to the amount they're coming in, right? 20 cars come every hour. Maybe they come every 3 minutes. They can let 1 car through every 3 minutes. So there's not really a line most of the time. But if you have 40 cars coming in an hour, you have them at a semi-often rate. So maybe there's a couple cars waiting in line, traffic is stopped, and then they let people through. But then if 49 cars are coming through, they can only let 50 cars through in an hour. So 49 come in that hour, they're really close to their limit. So on average, they're only going to be letting people through every 60 minutes in an hour divided by 50, 6/5 of a minute. So they're only letting cars in at a very slow rate. So you're going to get stuck behind a lot of cars who haven't gone through if you're coming into the construction zone. So what does that mean for part B as we approach 50? Well, as X is approaching 50, the length of the line is increasing dramatically. That's what our numbers are telling us, that as there's more cars coming through, 20, 40, 49, there's a lot more cars in the line for 15's 3.2, 48, waiting to get through that. So that is as X approaches 50, the length of the line is increasing dramatically. So that's a nice application problem for our rational functions.